All right. Back back home, I guess. So things should feel pretty good. I should get back into a cadence, hopefully no more sessions where it's an absolute struggle. Um, so yeah, should be back to normal here. Let's see here. What are we doing? OBS open. Yeah, let's do OBS. Not OBS. Let's do. Let me see here. Cool. And then let's see. What am I doing? What am I doing? What I'm trying to do here, flashcards. Yeah, we got a lot to review, so let's go over those first today so I don't run out of time again. And then maybe we keep reading for today. I need to... Okay, I know what to do. What I'll probably do today is I'll do the flashcards, and then I'm gonna write a list of features that we should work on for that data store to make it more sophisticated and to literally watch it get better. That's kind of the goal. Yeah. Okay. Oh my goodness, it feels good to be back. Okay, document model was just like, um, oh, there's one other thing I was thinking of. So, I think I have highlighters. Hmm. Hmm. So what are the advantages of the document model? Uh, Data locality, most things are stored next to each other. Hierarchical structures if you need them. And then schema flexibility. Yeah. Flexible, nested. I don't see locality here, but I'll say it's good. Polyglot persistence. I need to delete this card. Is when you use multiple solutions to achieve an optimal outcome. Oh, yeah. Whatever. A declarative language. So, declarative versus imperative. I think declarative is you declare what you want. So you tell the computer what you want and in what order, and it decides how to get it. The pattern of data, what conditions must be met, and how the data should be the system decided how to get the data. Good. Schema on read would be something like a document model where you're not really sure. The database itself does not enforce a schema. Yeah. Only interpreted when the data is read. Okay. What is the benefit of a declarative query language like SQL? It's an abstraction, so it allows for optimizations underneath the hood that affect everybody. Oh, simplifies logic and allows the database engine to optimize execution. So I'm not really saying what this is saying. So I didn't really, let's say this is hard then. It lets you specify what you want without describing how to get it, which simplifies the logic and allows the database engine to optimize execution. MapReduce is a programming paradigm that can be used to process large data sets across multiple machines. Yeah. What is the data model and why is it important? The data model is how we structure our data, and it's important because the way we structure our data is the way we're going to think about it and therefore dictate how we're going to solve the problems that we run into. Data and manipulate it acts as a contract, databases influencing design, maintainability, and performance. Impedance mismatch is when your storage data model does not match your application data model. Cool. 1.1 months. Let's go. Shredding is when we take a document model and turn it into many tables, splitting a document-like structure into multiple tables. How does the graph model represent data? With nodes and edges, nodes represents data, edges represents relationships. Yeah. A mem table is an in-memory table, such as a B tree, SS table, and it's temporary until we can create a segment file. Yeah, LSM tree. An SS table is a sorted string table. It's a type of mem table, and it maintains order, and it becomes a segment file after it reaches a certain size. That's right. Extract, transform, load is the process we use to put data into a data warehouse. A cluster index is when we store the data we want alongside the index, removing the need for the additional lookup. Let's say that's hard. I forgot that. That's like an important part, right? That's why we do it. B trees. B trees are balanced trees. It's not segments, it's pages. Pages are a fixed length, and it's always O of log n time for lookups, and then keys point to either data or references to another page. A heap file. A heap file A heap file is a file that stores arbitrary data using pointers to offsets for lookups. Not arbitrary data, sorry, where data is stored in no particular order, and then it's a common approach because it avoids duplicating data. Okay, so well, that's hard. A log structured merge tree. Yeah, that's the answer to this one. Okay. A concatenated index is There's a storm rolling in. A concatenated index is it where only some columns are located next to the index? Oh, that was stupid of me. I should have just like spent even 10 seconds thinking about it. Multiple fields into one key by appending one column to another. Orders defined by the index specifications. Yeah. Okay. Write amplification. When we write to a database, how many writes are required to perform that action, basically? How many times do we need to go to disk? Results in multiple writes to the disk over the course of a data's lifetime. Compaction is when we take a log file and we remove old or duplicate entries so we can condense stuff down. We can compact it. Throwing away duplicate keys in a log and only keeping the most recent updates for each key. A covered index. This is the columns. This is when certain columns are stored next to only specific columns. Let's say a subset of columns are stored next to the index. Cool. Decoding. So you have in-memory data that uses arrays, objects, to organize, instructs to organize data. But when we go over the wire, so like a network call, we need to pass a series of bytes to represent that data, and the transfer from in-memory data representation to like byte sequence, binary sequences, string sequences, whatever. I should figure that out. Is the decoding process. No, is encoding and going the opposite way. So sequences to in-memory structures, in-memory representations is decoding. Byte sequences, cool, to an in-memory representation, nice. Encoding, we just talked about it a lot, but it's in-memory representation to byte sequences. Nice. Oh, and we're caught up. Let's turn the lights on. It's getting real dark. Okay, so there's also this, right? Alright. Oops. I don't want this to go too long without progress on it. So what do we have here? That's right, we get some time. Oh, I need okay, so this is result actually no, this is fine. And if we go into benchmark, so this is benchmark right. We should probably okay, and now we should be able to come here. Why does this? Oh, because I pass a file in now. should probably expand these, right? Hmm. Um, okay, so maybe we ask, what did we learn, right? So I've read a few chapters now, and let's think about it. So if I'm writing, how come I can't think of anything? How do I do this? Let's. It's originally started for this. Let's see if I can't get inspo from here real quick. Mm. Mm. Okay, I need to do more research here. I'm not exactly sure how to progress at the moment. There is a path forward. I just don't know it yet. Um, Either way, this was honestly worth something. Setting up the test was good. I'm not done here. I'm not done here. There is more to do. I think I. Hold on. I think I lost the pillow. I'm trying to think of what I should do next here. Should I deploy this? So that I can test it on like a really shitty machine? I don't know. Okay, so we're gonna skip this for now. I think I need to think about this more. For now, let's go back to reading. I think this will be better use of the last 18 minutes because I'm not exactly sure what I want to do there. Okay. Okay. Apache AVRO is another binary encoding format that is interestingly different from protocol buffers and Thrift. It started in 2009 as a sub-project of Hadoop as a result of Thrift not being a good fit for Hadoop's use case. It also uses a schema to specify the structure of the data being encoded. It has two schema languages, AVRO IDL intended for human editing, and one based on JSON, and that is more easily machine readable. Our example schema written in AVRO IDL might look like this. The equivalent JSON representation of that schema is as follows. If you examine the byte sequence, you can see that there's nothing to identify fields or their data types. The encoding simply consists of values concatenated together. A string is just a length prefix followed by UTF-8 bytes, but there's nothing in the encoded data that tells you that it is a string. It could just as well be an integer or something else entirely. An integer is encoded using, to parse the binary data, you go through the fields in the order that they appear in the schema and use the schema to tell you the data type of each field. This means that the binary data can only be encoded correctly if the code reading the data is using the exact same schema as the code. So this is like backwards forwards compatibility. Any mismatch in the schema between the reader and the writer would mean incorrectly decoded data. So how does AVRO support? Okay, if we completely further with AVRO, when an application wants to encode some data to write it to a file or database to send it over the network, it encodes the data using whatever version of the schema it knows about. For example, that schema may be compiled into the application. This is known as the writer schema. When an application wants to decode some data, read it from the file or database, receive it from the network, it is expecting the data to be in some schema, which is known as the reader schema. Yeah, okay. The key idea with AVRO is that the writer schema and the reader schema don't have to be the same. They only need to be compatible. When data is decoded, read. The AVRO library resolves the differences by looking at the writer's schema and the reader's schema side by side and translating the data from the writer's schema into the reader's schema. The AVRO specifications defines exactly how this resolution works. And wait, what? For example, it's no problem that the writer schema and the reader's schema have their fields in different order? Because the schema resolution matches up the fields by field name. If the code reading the data encounters a field that appears in the writer schema but not the reader schema, it is ignored. If the code reading the data expects some field but the writer schema does not contain a field of the name, it is filled with the default value declared in the reader schema. This seems like really specific. I don't know. This is not a long chapter. Huh. Okay. The key idea with AVRO is that the writer schema and the reader schema don't have to be the same. They only need to be compatible. When data is decoded, read, the AVRO library resolves the differences by looking at the writer schema and the reader schema side by side, and translating the data from the writer schema into the reader schema. Okay. The keyboard is so freaking nice, man. So it's no problem if the writer schema and the reader schema have their fields in different order, so that's still compatible, because the schema resolution matches up the fields by field name. If the code reading the data encounters A field that appeared in the writer schema but not in the reader schema, it is ignored. If the code reading the data expects some field but the writer schema does not contain a field of that name, it is filled in with a default value declared in the reader schema. Okay, so I feel like it's pretty dang close. A little confusing. Alright, this is a little confusing. Let's just stop here as a good stopping point. Right on.